Hi students, 12th standard chemistry unit 5 coordination chemistry. So we have seen the metal carbonyls. In this session I am going to teach you the stability of metal complexes. Okay, so the stability of metal complexes can be interpreted in two different ways. The first one is thermodynamic stability. It can be of two types. The very first one is thermodynamic stability and the second one is kinetic stability. Okay, this thermodynamic stability refers to the change in free energy. When the complex is formed, the change in free energy refers to the thermodynamic stability. Okay, it refers to the change in free energy. It can be represented as del G. Okay, then this kinetic stability refers to the ligand substitution in a reaction. Ligand substitution in a reaction. Okay, so thermodynamic stability refers to the change in free energy when the complex is formed. Kinetic stability refers to the ligand substitution reaction. Okay, this ligand substitution reaction is of two types. One is labile and the second one is inert. What it means? Okay, in some coordination complexes the ligand substitution is very rapid or fast. Okay, if it is fast means that is called labile complexes. Okay, in some ligand substitution reaction it is very slow. If it is very slow means that is called inert ligand substitution reaction. Okay, so this is the very simple classification. Then we can go for the stability constant. Okay, stability constant is represented as beta. Okay, in order to explain the stability constant, just assuming this reaction, here copper reacts with ammonia to form a complex ion. It is a coordination complex. Okay, so what is the name of this complex? Tetraamine copper 2 ion is the complex. Okay, here the reactants converted into the product. Here there is a equilibrium between the reactants and the product. Okay, this symbol indicates the equilibrium. There is a equilibrium presence between the reactants and the product. How can I write the stability constant for this reaction? The concentration of the product or the concentration of the complex divided by the concentration of the ions or the concentration of the reactants. So let me write the stability constant first. So the concentration of the complex, this is the product and this is the reactant. Let me write the product first. CuNH3 4 2 plus. So this is the concentration of the product divided by the concentration of the reactant. Cu2 plus NH3 4. Okay, in this way I can write the stability constant for any given reaction. Okay, so from this what we can infer from this equation means whenever the complex, the stability of the concentration of the complex increases, stability also increases. Whenever this is the product, whenever the concentration of this complex increases, stability increases. Okay, therefore if stability increases, what will happen? Simultaneously the stability constant will also increases. Okay, we can conclude this: whenever the concentration increases, stability increases. Okay, greater the concentration, greater will be the stability constant. Greater the concentration, greater will be the stability constant. Okay, so all the coordination compounds are stable in their solution. If I am taking the beaker with the solution and I am adding any of the coordination compound to it, what will happen? to some extent some of the coordination compounds get dissociated, okay, but they are stable in their solution form, okay. So, in aqueous solution when complex ion is dissociate, there will be the equilibrium. So, let me write the opposite reaction for this reaction. So, I am going to take the complex ion which is nothing but Cu NH3 4 2 plus. So, this is the complex ion. If I am adding the complex ion into the solution, what will happen? To some extent this complex ion, it will get dissociated. So, let me write the equation for this. So, Cu2 plus NH3 4, okay. There is a equilibrium between the undissociated complex and the dissociated ions, okay. What is happening here? There is a equilibrium arises between the undissociated complex with dissociated ions, okay. So, this what we can infer from this, okay. The dissociation equilibrium constant, which is nothing but alpha. How can I write the alpha here? So, this is the reactant, this is the product that we are getting, no, the product divided by the reactants. So, let me write the alpha here, alpha which is nothing but the dissociation equilibrium constant, or otherwise it can be called as instability constant. So, I can write like this, Cu2 plus NH3 4 divided by the complex ion Cu NH3 4 2 plus, okay. Finally, the overall stability constant. How can I write the overall stability constant? The dissociation equilibrium constant is the reciprocal of, this is called what? Stability constant, okay. Is it clear for everyone? Yes. Thank you.